What is up, guys? In this video we'll be breaking down how to protect equipment from wear and chemical attack at the same time. And for this example, we'll solve the problem of a material hopper seeing aggressive wear for the media going through it and chemical attack from sulfuric acid. To get to our solution, there are two core functions: wear resistance and chemical resistance, and each is solved very differently. So in this video, what we'll do is break down each one and hopefully arm you with the information you need to protect your equipment from both. Now, real quick, if you don't know me, at 22, I got my degree in chemical engineering, and since I've spent nearly a decade studying, modifying, and implementing polymeric lining and composite technologies for the industrial sectors. And polymeric is just a fancy word to make me sound smart. It refers to resins like epoxies, urethanes, and the like. In that time, I've been a part of and led projects from $500 to $500,000 in material alone, and I make these videos to help maintenance and engineering teams, with the goal being to help increase understanding of and properly select coatings, linings, and composites for industrial processes. Diving into the details, again, there are two core functions your lining needs to be able to accomplish. On one side of the aisle, we have our wear resistance, and on the other side, we have chemical resistance. And we'll cover each one separately, and then at the end, show you how we combine them for maximizing our performance in service. Beginning with wear resistance, what is it? In the industrial sectors, wear resistance is a bundled term for abrasion and corrosion. Defining our terms, abrasion is a wear mechanism for hard particles rub against a substrate and remove material. For erosion, it's a wear mechanism where the substrate naturally loses material over time. So we have our terms, and abrasion is a more active process while erosion is a more passive process. And the act of solving wear problems by themselves is worth a whole series of videos by itself, which you guys will get in the near future. But to summarize it in as few words as possible for wear, the harder the better. And I'll leave you guys a few seconds to make a joke about the harder the better. The question becomes, how do we achieve this? And I like to use functional additives like ceramics and carbides. And the reason behind this is, short of diamonds, these are the hardest materials available on planet Earth. You're probably thinking, all right, cool, Nick, why does that matter? Think of wearing as a scratching away of material. So the harder it is to scratch, the longer it will last in a scratching or a wearing environment, regardless of it being abrasion or corrosion. And what you can see here on your screen is a picture of aluminum oxide, which is a ceramic, and this is in powder form. This is what we use to blend into the linings, but this is an example of it. And to the naked eye and even to the touch, it feels soft, but it is extremely hard. Now, some time ago, I came across a hardness scale that showed the hardness of steel versus the hardness of ceramic. And so for a 1045 carbon steel, this has a Rockwell C hardness of 3, and you can see that circled here, whereas the ceramic has a Rockwell C hardness of 63. And in this case, I chose aluminum oxide. There's some variance here, but chose aluminum oxide. And you may be thinking, all right, well, 3 to 63, if carbon steel's a 3, it's still, pretty hard given the scale that we're looking at. But this scale is actually nonlinear. So a 63 hardness compared to a 3 hardness for your carbon steel is actually going to be about 10,000 times harder, relatively speaking, given the way this scale works. The reason I show you this information is to show the magnitude or the step change difference in what a ceramic can offer over a steel substrate. And it's for this reason that we use ceramics in our epoxy linings for applications like this. And so in this case, this is a chute that it sees a very high amount of wear. When running, it'll see about 3,000 tons of material in a given hour. And so they actually put ceramic tiles in this, and now with the ceramic lining, what we can do is we can repair and protect the steel where those tiles have failed, as opposed to just using steel. So to boil this down, if you need to resist wear, a ceramic lining is a great answer because of the increased hardness that we can achieve. And I want to be clear, it isn't the only answer, but it's an answer and they work great, and it's one that I use quite frequently. With that, we've solved puzzle number one, or problem number one, which is how do we achieve our wear resistance. Switching gears to our acid or chemical attack problem, we solve this very differently. Chemical attack on resins comes down to chemical compatibility. And it's important to note here that with wear resistance, let's just pick some arbitrary numbers. Let's say we have a rock and then we have a ceramic, right? So one's harder than the other, one will last longer than the other, relatively speaking. Or if we take a ceramic at a 1/4 inch or we take a ceramic at 1 inch, it's 4 times thicker, it's going to last 4 times as long. With chemical attack, that generally is not going to be the case. Do we have some differences in how long a material can last? Absolutely. But when we get into chemical compatibility, it is more a black and white. It works or it doesn't work. And again, I'm speaking in generalizations here. But if I take a general purpose epoxy and put in nitric acid, it's not going to work. Even Novolac epoxy isn't going to work. But if I go with a halogenated resin, where I step into something that is compatible, it can work, I don't want to say indefinitely, but for a very long time. And so I want to make sure we delineate the difference between how we solve wear resistance and how we solve chemical resistance. With that bit of information in mind, this is a containment here that's seeing acid attack. And again, it's important to note that whereas this failed more just because of over time, I want to say this was in service 20 years, so it actually went quite well. You can see how this material starts to break down. And it's important to note that where with the ceramics and with wear resistance, going thicker can increase longer service life. When we're dealing with chemical compatibility, going thicker won't solve that problem the same way. If it's not compatible, it's not compatible. Think about it like this. If marshmallows can't hold up to sulfuric acid, then whether I put 20 thousandths of an inch on or 20 miles on, the acid's still going to eat through the marshmallows, and that's how we should think of this. So now diving into the resins themselves, general purpose resins cover a wide range of chemicals at low to moderate concentrations relative to their intrinsic strength. And what do I mean by that? So epoxies naturally are very good from a chemical resistance perspective. They're not great against everything, and they're not going to be great against all concentrations. But across the board, they have great chemical resistance to a wide range, from acids to bases and everything in between. But as we switch to our more specialized resins, we can increase compatibility for specific subsets of chemicals. So again, in this example, we're talking about sulfuric acid. And so with that, as concentration goes up, we need to get more specialized with our resins. So what kind of specializations can we do, or what formulation tweaks can we make? So some examples, broadly speaking, from a resin perspective and not even just from an epoxy perspective, would be if we're dealing with, let's say, oxidizing acids, something like nitric acid or chromic acid, where we have very quick and rapid breakdown of an epoxy, we can switch to a halogenated resin, so that's something that's chlorinated or brominated, and pick up a great deal of chemical strength there. Let's say we're dealing with solvents, something that naturally will go after most resins, including epoxies. We can switch our curing agents to be more monomeric in nature, and with that we pick up solvent resistance. And lastly, let's say we have something that's higher temperature, or we're dealing with high pH up over 13 or low pH down below 1. Think acids, think bases, anything strong. What we can do is we can switch the curing agent on our epoxies to aromatic curing agents, which gives us more strength both mechanically and chemically. And so to give you guys an idea, and this is going the route of the nerd, is this is a bisphenol A resin. And so this resin here is what I would consider a general purpose epoxy. And I want to be clear, general purpose doesn't mean it's a bad epoxy. I just say that in terms of it is a workhorse epoxy that's used in a lot of things to cover most environments. And so this is where we get into our various curing agents. So in the top left here, this is DETA. This is something that's going to be more monomeric in nature that can help us pick up solvent resistance. As we go down here to PACM, that's something that's going to be, it's not technically aromatic, but it's cyclic in nature, so we're going to pick up more chemical resistance and often more mechanical strength as well. In this example, we've been talking about having to defend against sulfuric acid. So the route that I would take here is switching to a Novolac resin, which looks just like this. And for you guys, you'll notice here, 1, 2, 3 points for this material to bond or to cross-link with when it cures. And compare that here to our 2 points to bond with, and that's where we can pick up an additional link, which is going to make it stronger. And then also, we can jump into something like an MXDA hardener, which is going to give us our 2 points here. These are going to be our active amine sites. And then that's where we can switch to our hardener here. And this is going to be our 2 active amine sites for curing in our aromatic hardener. And this is MXDA, which is a great hardener across the board for a lot of different things. Now you're probably at the point, well, Nick, again, that's cool, but I don't think a manufacturer is going to give me their formulation so I can check this. You're 100% right. So what can you do for resin selection? And while most, if not all manufacturers won't give you their formulation, they do have guidelines on what each resin is suitable for. So in our case, we have wear and are dealing with sulfuric acid, and most Novolac epoxies are going to be suitable for sulfuric with varying degrees of performance. So your manufacturer rep should be well versed in selecting between their available options. Again, lean on your rep. These are guidelines to follow. So again, to solve puzzle number 2, part number 2, how do we get over the acid problem? This is where, again, we're going to use our Novolac here with a good hardener. I chose MXDA. There are a number of them out there that you can use. And sorry if you notice my eyes just got red. I just had a coughing fit and almost died. So here we are. But let's now combine our solutions to each puzzle for the bigger problem. And again, that problem is, how do we protect equipment exposed to both wear and chemical attack? In this case, high media flow with sulfuric acid. So what we're going to do is we're actually going to combine our answers in reverse order. And the reason is, without the chemical compatibility that the resin gives, right? So in this case, the Novolac and the MXDA, that resin's acting as a binder to both stick to the wall and hold the ceramic on the wall or the substrate, whatever we're doing here. And so if that doesn't hold up, what it'll do is it'll render the ceramic useless because nothing's going to stick to the wall, so the ceramic doesn't stick, so we don't have chemical compatibility, and we certainly don't have wear resistance. So again, to solve this, select the most suitable resin for the acid at hand. So for sulfuric, again, we chose our Novolac with their aromatic curing agent. And generally speaking, your manufacturer will have a specific product line or resin lines for various applications. So think, generally, this is our acid line of products, or this is our increased chemical compatibility products. Step 2 is the easy part. Now that we've selected the resin, select a formulation that has that resin that's already been blended with ceramic additives. There might be some slight modifications, but this is going to solve the back end of that. And so with that, we've combined 2 solutions into one. We've created an epoxy lining system capable of resisting acid due to the resin selected, and our functional ceramic additives provide excellent durability to wear and tear. Hope this was helpful, something you can use in your day-to-day operations. I have one ask. There's someone who could benefit from this information. Please like this. Please share it with them. That way we can get the message out. My goal is to be here to help you guys, especially because there's a lot of different information that flies around. So I hope to give you all the knowledge that I have and maybe see you out in the field. So until we see each other again, stay safe. Godspeed.